Okay, so let's go through and review some of the concepts from last time relating how the forces and the winds are related. So let's start off at upper levels where we know that the friction is going to be small. So we're just dealing with two forces, our pressure gradient force and the Coriolis force. And let's suppose that we've got an upper level chart like the one shown here. And remember, when we're dealing with an upper level chart, what we're showing are contours of height on that chart. So these lines here are the contours of the height. And so in this specific case, we've got higher heights down here to the southeast, and we've got lower heights up here to the northwest. And suppose that from this information we want to infer the forces involved in the winds. Well, what we've got here is height information. So the one thing that we know is going to be the pressure gradient force, because we know that the pressure gradient force is going to go perpendicular to the height contours from higher heights towards lower heights. And so it's going to be something kind of like this. Perpendicular to the contours from higher to lower. We also know that if it's a large-scale flow, then the forces come into equilibrium, which means that our pressure gradient force and the Coriolis force are going to be roughly in balance. So our Coriolis force then has to point the other way in roughly the same magnitude to keep everything in balance. So now we just have to figure out the winds, and once we know the Coriolis force, we can also figure out what the winds are going to look like, because we know a couple things about the Coriolis force. So for instance, we know that the winds and the Coriolis force are perpendicular. Right? The force is perpendicular to the wind direction, which in this particular case means the winds are going to have to be along the contour line so as to be perpendicular to the Coriolis force. So then we just have to figure out which direction along the contour line, towards the northeast or towards the southwest. And to figure that out, we have to remember that when we're looking downwind in the direction of the wind, the Coriolis force is going to be to our right. So let's start off by thinking about the northeast direction. If we're standing at this dot and we're looking towards the northeast, then which direction is to our right? Well, the direction to our right in that case is in fact going to be the southeast, which is the direction that the Coriolis force points. So in order to get the Coriolis force to be to the right of the wind direction is going to have to be to the northeast. So this is going to be the general result at upper levels when we're not dealing with friction. We're going to have the winds being along the contours with higher values of the height to our right, because that gives us the right configuration between the wind and the Coriolis force. Okay, so let's suppose we have something like this. So again, this is going to be a pattern of upper level heights. These are our contours of height. And suppose in particular we ask the question, which of these 2 points here is going to have the bigger wind? Which one's going to have a stronger wind? And so as usual, we'll assume that the heights are higher to the south, where it's warmer, and the heights are lower to the north, where it's colder, causing the layer to contract, giving you lower heights. And we go through and we do this step by step, just like we did before. So again, the information we're given is the height information, and the thing we can infer from that is the pressure gradient force. So we'll start off with this point on the left, and we draw in our pressure gradient force, and it looks something like that, perpendicular to the contours, high to low. And then we go over to the point on the right. The direction for the pressure gradient force is going to be the same, perpendicular to the contours from higher to lower. We just have to think about the magnitude, how big it's going to be. And for that, you have to remember that when the contours are closer together, that means that the pressure is changing more quickly from one place to another, because you cross the contours more quickly. And when the pressure changes more quickly, you get a bigger force. So when the contours are closer together, we get a bigger pressure gradient force. Say something like that. Okay, so we're going to have a bigger pressure gradient force where the contours are tighter. Again, Coriolis is going to be roughly in balance, and so that means that the Coriolis force is going to point the opposite direction with roughly the same magnitude. So first the point on the left, roughly in balance, and then the point on the right, roughly in balance. Again, knowing the Coriolis force, that also tells us information about the winds. And so again, we have to have the Coriolis force to the right if we're looking downwind. So let's figure that out first. So if we put ourselves at this point here, we know the wind is perpendicular, so it's either to the east or to the west. And if we put ourselves at this point and we look to the east, then to our right is in fact to the south, which is the direction of the Coriolis force. If you're looking east, then to your right is south, which is the direction of the Coriolis force, which means the wind had to be to the east. Oops. The wind had to be to the east. It's going to be the same deal over here at the other point. The wind has to be to the east so as to give the Coriolis force in the right direction. But because the Coriolis force is bigger, that means the wind has to be bigger too. Remember that the Coriolis force is proportional to the wind speed. So a bigger Coriolis force means you must have also had a bigger wind. So our wind's got to be the same direction but bigger at this point. So in the end, then, what we've shown is that places that have tighter height contours are going to have bigger winds. Places that have the height contours closer together are going to have bigger forces, and the bigger forces imply bigger winds as well. You can kind of think of this as being kind of like a flow in a stream. And if you have a flow in a stream, and let's say that these two lines here are the banks of the stream, then when the flow is going through when the banks are far apart, then the flow tends to be fairly slow. But then when the stream bank comes together and the stream narrows, then the speed picks up quite a bit. Where you have narrows in your stream, that's where you also have your rapids. That's where it goes fast. It's the same kind of thing here. It's the same kind of relationship. When the contours are further apart, the winds are weaker. And then where the contours get closer together, that's where the winds are going to be bigger. Okay, here's an example. I'm showing a 300 millibar chart. So this is upper troposphere. And the black lines here are your height contours. And the blue color is the wind speed. So places that are darker or blue and darker blue have stronger winds. So it's going to be fast winds up here and then slower winds where it's white. And then these little barbs back in the background here, these things are actually the winds. You can think of these as arrows with feathers. We've got feathers on the backside, and then the arrows point in the direction of the winds. It might be a little bit hard to see on the screencast, but like at this point here, the winds are going towards the north-northeast, or actually east-northeast, I guess. And so the feathers are on the backside, and then the points are the direction of the wind motion. And what we can see from this is that the same basic relationships we were just talking about hold. In particular, in general, the winds are pretty close to being parallel to the contours pretty much everywhere. Right? We can follow along this contour here, for instance, say starting over here, and the winds are pretty much parallel to the contour. The winds are following the contour here, just like in our previous example. And then the second thing we see is that places that have contours that are close together are going to have faster winds. So right in here, the contours are really close together, and the winds there are faster. And same thing over here. The contours are closer together and the winds are faster. And this is generally true. I mean, this wasn't a special case. This was just a case from the day that I was teaching this material, either this past spring or the spring before. I can't remember. And so, I mean, pretty much any time you look at upper levels, you're going to see these relationships with the winds along the contours and tighter contours being faster winds. One thing I will note is that if you look really carefully, I haven't looked that carefully on this figure, but the relationship between the spacing and the winds, while it's generally true, there are some subtle variations due to things we didn't talk about. In particular, it turns out that the curvature of the contours also matters a little bit. That's more than we're going to get into, but it's a secondary effect. It doesn't matter that much. Your position north-south also matters a little bit. If you have the same contour spacing here to the south, it'll give you a little faster wind than the same contour spacing up here in the north. But again, that's a secondary effect. To a first approximation, where you have tighter contours, you get faster winds. Okay, so now let's go back down to the ground. And when we get to the ground, it's basically the same deal, except at the ground we have to worry about friction. So it's basically the same deal here, but because we have friction, the winds aren't directly along the contours typically. They tend to cross the contours a bit towards lower pressure. And again, what's going on is that your pressure gradient doesn't change. That's just determined by the pressure contours. But because you have friction, the winds are a little bit slower. And if the winds are a little bit slower, the Coriolis force is a little bit weaker, which means things aren't in balance anymore. And the pressure gradient force is bigger, so it can pull the winds a little bit in the direction of the pressure gradient force, right? And so the winds aren't directly along the contours, they're a little bit across the contours towards low pressure. And again, generally speaking, when we look at surface maps, we see this. So it might look something like this. This is a schematic here. Suppose we had a low pressure zone. Generally speaking, the winds are going to be sort of along the contours, just like we've been talking about, with higher values, with the higher pressure values to your right? So winds along the contours, higher pressure to your right. Except because we have friction, the winds actually cross the contours a little bit. And around the low, it's counterclockwise as we expect, but because of friction, they cross the contours a little bit. One thing to point out here is that when you have the winds crossing the contours like this around a low center, that means you've got a little bit of convergence into your low. So there's some component of the wind that's going into the low. It's not just going around, it's kind of spiraling into the low. You've got a little bit of convergence into the low. Here's an example surface map showing isobars. The isobars in this case, remember on the surface we look at isobars, lines of constant pressure, and the isobars are the black lines. We've got regions of high and low pressure indicated. And again, these little lines here, these little barb-like things, these are the winds. And again, you can treat them as like feathers and arrows, where you've got feathers on one end, and then the pointy end is the direction that the wind is going. And again, this wasn't any special case. This was just the case on the day that I was teaching this. But you can see the basic ideas in most of these things. For instance, we've got a low pressure center here, and generally speaking, the winds are going around the low pressure center to the counterclockwise, in the counterclockwise direction as we expect. But in most points around this, the winds aren't going directly parallel to the contours. They're crossing the contours a little bit towards low pressure, which is what we expect. Again, up here, winds are crossing the contours towards lower pressure, crossing the contours towards lower pressure. So basically, around the low, but with some component crossing the contours. And the end result is you get some convergence into your low. You can see the same thing up here. It might be a little bit hard to see, but the winds are sort of going along the contours, but they're also crossing towards lower pressure here and towards the low center. And of course, it's the opposite if we look at high pressure zones. So for instance, with this high pressure here, the winds are going clockwise as we expect, and they're sort of following the contours, but they're also going across a little bit, right? They're going across towards lower pressure, which in this case means outwards. So around the high center, the winds are actually diverging a little bit, spiraling out away from the high. So here's a schematic showing all these ideas together. This one's from the text. And the one on the left is comparing what goes on at upper levels compared to what goes on at the ground. At upper levels, we just have pressure gradient and Coriolis to worry about, and the winds are parallel to the contours. At the ground, we also have to add in friction, and as a result, the winds cross the contours a little bit towards lower pressure. So if we had a configuration with a low center at the ground and a trough above it, then in that trough, the winds are basically following the contours. But at the ground, the winds are more or less following the contours around the low, but they're also converging into the center a little bit. And if you had a high, same idea. Upper levels, if you have a ridge, the winds are going along the ridge, parallel to the contours. And at the ground, they more or less circle around the high like we expect, but they're also crossing the contours towards lower pressure, which is outwards a little bit. So there's some divergence. Okay, so let's pay a little bit more attention to this divergence and convergence thing. So again, at the ground, where we have friction, if you have a low center, the winds are going to be converging into the low a little bit. Right? They're crossing towards lower pressure, converging into the low center. And if you have a high, it's going to be exactly the opposite. Their winds are going to cross towards lower pressure, which is diverging. I'm going to switch the colors here on this guy. Okay. So generally speaking, around high pressure, air diverges, and around low pressure, air converges at the ground. Now this has implications then for what goes on above it. Because if you have air that's converging into a low center, that air piles up and it kind of has to go somewhere. And the place it goes is upwards. It's kind of like, you can think of this as sort of when you squeeze a toothpaste at the bottom, when you pull it together or push it together at the bottom, that forces the toothpaste inside to go up. It's going to be the same kind of idea here. If we squeeze things down here at the bottom by converging the air, that's going to force the air in the middle to go up. And by contrast, if we go over to the high pressure where the air is diverging, now we're pulling the air apart. So we're taking the air that's in the middle and pushing it outwards. And as a result, air is going to be pushed downward from above. It's going to be pulled into the place where you're diverging from. So when we have convergence, we're going to drive the air upwards. And when we have divergence, it's going to pull the air downwards. So the rule of thumb is low pressure centers are going to feature converging air and then rising air. On the other hand, if you have a high pressure center, that's going to feature air that diverges, and above it, it's sinking. Now this is important because if you remember when we talked about clouds, the way you get clouds is have rising air. Places that have rising air tend to be cloudy, whereas places that have sinking air tend to be clear. So, relatively speaking then, cyclones or low pressure centers which have rising air above them are going to tend to be cloudy places. So cyclones are cloudy and rainy weather. While anticyclones, the high pressure zones, they have air sinking above them, and so they're going to tend to be clear and sunny. This is actually the rule of thumb that we started all of this back when we back when we first talked about cyclones and anticyclones, that low pressure zones tend to be cloudy zones and high pressure zones tend to be clear and sunny. And it just has to do with this convergence or divergence at the ground. Low pressure centers, air is converging, which causes the air to rise, and rising air produces clouds. On the other hand, the high pressure zone, the air is diverging at the ground, which draws air downward from above, and sinking air tends to be clear and sunny. Okay, so at this point, we've more or less finished all of the basic concepts, the fundamental concepts that we need. And so for the rest of the course, we're actually going to go through and talk about different kinds of circulation systems and apply these concepts that we've learned to discuss their features.